Hello everyone, today we will be talking about transistors. Now, there are two main kinds of transistors, which are BJTs, which usually come in a small package like this, which I'm holding right here and I'm shaking, and MOSFETs, which come in a larger package. For now, I'm going to be talking mostly about MOSFETs throughout the video. So I have built up a little circuit over here, and as you can see, it is using a MOSFET. Now, a MOSFET transistor has 3 pins. So if I can draw this, it has the schematic symbol of a MOSFET looks like this. And it has 3 pins. A gate, a drain, and a source. A source, as you can see, and sometimes they like to put an extra diode over here, and this is basically a MOSFET's internal body diode, as they sometimes refer. And in fact, I can show an example over here with this circuit. So, for example, maybe if I disconnect the power to maybe reset it, or perhaps bring the gate low, because that's another little trick with MOSFETs, because when you when you pull the gate high and then just leave it floating like that in a high resistance state, it stays on, because unlike BJTs, where the amount of current flowing into the base determines its on resistance, or how on it is, as I like to say, what determines the state of the MOSFET is the voltage between the gate and the source. And the reason why the light stays on, or the drain source path continues to stay connected, is because there is a little monster capacitor that sits between the gate and the source, and it's always there. In fact, there are capacitors there are leakage capacitances, as people like to say, between the gate and drain, gate and source, and drain and source. And this gate and source one is what is, and this guy is an absolute monster. Because, first of all, if the gate is left in a high impedance state or a high resistance state, then the gate, if it's high, it will still remain high because this capacitor is charged up and is still keeping the MOSFET closed. And to turn it off, you can just use a capacitor between the gate, and you can use a resistor between the gate and the source to turn it off like this. And it's still kind of annoying because that capacitor likes to charge up. Also, since there is you can add a resistor between the gate and the source, which is just connected to ground, so in this case it'll work. And you can see it functions just correctly, like so. And this resistor basically, it also acts like a pull-down resistor, keeping the gate low whenever the switch is not pressed. But let's move on, because if we add a resistor across here, well, the resistor across there is fine, but since there's a little capacitor here, for a very short period of time, if you want to put a signal on the gate, the capacitor resists a change in voltage. So it will draw a lot of current for a very short period of time to charge up the gate capacitor and make the MOSFET do its thing. So that creates an issue when the gate is being controlled by a simple microcontroller that can't really handle a lot of current on its outputs. if you're switching the gate on and off really, really fast, it can draw a lot of current for a decent amount of time, and it will eventually damage the microcontroller. And you can add a resistor in series with the gate. And this does work for low-frequency switching tasks, but since the resistor makes the capacitor take a longer time to charge, it makes the MOSFET a lot slower in its task. So if you want to do an extremely high-speed switching, you need to have a MOSFET driver, and the MOSFET driver basically just sits between the gate and the whatever output of whatever you want to control, whatever's controlling it. And basically allows a quick amount of current to flow, a large amount of current to flow in the gate to charge the capacitor up quickly, so that you don't draw a lot of current from the microcontroller, and so that your microcontroller doesn't die, or whatever you're switching doesn't die. So another thing about these MOSFET transistors, they are very efficient electrical switches. So, some MOSFETs I've seen in the datasheets can handle over 47 amps. I'm not totally sure if that's a continuous current or what, but because they're very efficient. When they are fully turned on, they have a very low resistance. It can probably be as low as like 1 milliohm. And that's a very big advantage for MOSFETs, because even if you got a lot of current flowing through it, the power loss is very minimal, and it will only heat up slightly. And thanks to its large package size and its ability to be mounted to a heatsink, it can handle a lot of current if set up correctly. Unlike the BJT transistor, which is less efficient and usually comes in a much smaller package, which can't be mounted to a heatsink. So it's got less thermal mass to deal with, less heat sinking area, and it's just not very good for high power applications, which is why we use MOSFETs most of the time, for example, in switching power supplies. And that's about all I have to say about MOSFETs, and in fact, thanks to the MOSFET's good efficiency, there is something called an active rectifier, which takes a full bridge rectifier, which is normally made up of several diodes. I mean, you can have it like this, but normally, or in a lot of cases, it's going to be an individual. It's going to look something like this, with 4 pins. You can get full bridge rectifier chips like this, which basically is a full bridge rectifier, the 4 diodes in a single package. And basically what the active rectifier does is replace the diodes with MOSFETs, and has a special chip that turns on the MOSFET gates at just the right time, so that it can switch the loads nicely and convert AC to DC very efficiently. And that's about it for this video. Bye-bye.